Okay, welcome back. So I'm recording now, Tracy and Sheetal, just that you're aware. So we are discussing as the first question, we're going to discuss lab number 7. Both Sheetal and Tracy asked for this to be discussed in more detail. So let's go and have a look at this. So we're doing summer 22, classes 7 and lab. So we are having from the lab essentially randomized controlled trials is the main topic. And just a second. Okay, so I think the general overview was hopefully quite clear. So essentially you are opening the faraway package, which in essence, oops. So the faraway package, in essence, is also explained in the faraway paper, which I hope you all have seen. And I'm trying to find it. It was actually so the very same paper was also shown in the faraway paper and the faraway book, essentially, that also discusses the same kind of example. So you basically have a yield, which is a numerically variable. You have blends that distinguish the different crop variations, and you have the treatments from A to D. So you basically want to see what has a stronger effect on the actual yield, and you distinguish between treatments and you distinguish between blends, because blend variations do have different variations in the corresponding yield. So the way you would do that, so you do here the pivot table, essentially allows you to have a better overview over your data. So it basically organizes it as per the different treatment levels and as per the different blend variations. So you see the respective blends and treatment factors basically resulting in yields. And you see already that there's quite some variation in the actual yield. So this you want to understand in a little bit of more detail. So you basically build first linear regression model where you basically build linear regression where yield is a function of treatment and blend. This being done, you can look then at the actual model. So now you know that essentially there are treatment differences that essentially vary from 1, 5 to 2 as compared to treatment A. So these are actually differences where you actually have a higher yield as per these treatments. In addition to that, you also have here the blends where you see differences according to the blends that are essentially in reference to blend number 1. So you see that there are differences for all of the blends as compared from 2, 3, and 5 to blend number 1. But you don't have significant differences in terms of treatment. So one of the explanations for that could be that there's an interaction and you're missing the interaction. And you're building now 2 fits. You're building one fit where you just look into the differences between yield and data. And you can always map this out where you can, where you look at the respective models yourself. So you see that these are essentially corresponding with these differences that you have seen here with a different intercept. So if you do the same with summary fit 0, fit 1, you can see -9, -7, -4, -10, -9, -7, -4, -10. So these are the group differences. So now you want to see whether the addition of a main effect of blend essentially has increased has increased your understanding, and whether these are actually significantly different. So the prediction as per your model where you have treatment and blend included, whereas you have your model where you have yield only as a function of treatment. And you see that the inclusion of blend has actually given you significantly more explanatory, let's call it explanatory power. So you essentially you have smaller, you actually have a smaller residual sum of squares. This means that the inclusion of blend has actually allowed you to explain more of the variations you see between the various different cells in your pivot table. So, and now in a second step, you basically do the same exercise with the model where you only include your treatment. So this is essentially what you do here with fit 1, where you compare essentially whether the inclusion of blend and treatment were. So the only not included variable here in model 2 is treatment. So you're basically comparing blend only as an explanatory variable to treatment and blend. And this here, you essentially see that there's no significant difference. So that essentially leads you to the conclusion that actually the treatment was not significantly associated with your yield, whereas your blend clearly was, which is hand in hand with the interpretation from your overall model, where you essentially see no significant differences. And the significant differences basically indicate here that only blend matters. So now you go in the next level, you actually go one further, and you're trying to predict these data. By essentially predicting now two things. So you have here your yield as a function of your treatment. And you see that there is some trends, but we know from the model that there are no significant differences. So now we're seeing this same outline here, in essence, where we see quite some variation with some particularly strong outliers, with blend 1 being here pretty much the leading yield, which we also have seen from various other models, where we basically see here blend 1 as compared to blend 5 has here a difference of -10 yield. Although the metric is, I'm not sure what the metric was. So you see confirmed what you have seen in the models. And here essentially you're just looking at the residuals. Here you see, yeah. Oh, no, everybody's running. Great. Welcome everybody. So here essentially you see here the QQ plot that essentially allow for you to judge the residuals as compared to the prediction of your model. And here with the QQ plot, you see an overline between the actual sample quantities versus the theoretically or predicted quantities. That's essentially how you look at residuals over time. So you see quite some homoscedasticity, so it doesn't vary that much. And then in the next step, in the last step, you can now, you get an AOV. So you build an ANOVA, and you use then this ANOVA to look at Tucky's honest significant differences, which is, I don't know whether you looked at the specific, let's look at the interpretation of those. So you basically see, just like we've seen in earlier comparisons and earlier examples, you see differences between both. That's the summary. So you see here essentially the significances between the respective estimates you see the degrees of freedom, you see the sum of squares, and you see that as per the F statistic, here by the F value, you essentially get a significant difference as per in the comparison as per blend. So in a Tukey-honest significant difference test, you essentially compute a so-called Tukey's Q. And if you look at this specifically, you can always look at all these objects that you are computing. So you see here the difference is depicted with the actually lower and upper 95% confidence intervals and adjusted P value that essentially allows for you to look into differences between the respective combinations. So again, if you take here plot Tukey and you display Tukey, you essentially see that there are not dramatic differences, but there are influences of blend. Here, for example, that you did not see with your treatment, but you see them with the blends, which essentially is not apparent here with your treatments. And yeah, so that was the discussion of the treatment. So essentially what you do then with a Tukey, you basically look at 95% confidence intervals, and you're basically comparing them within your characteristics, and you're basically trying to compare them within those groups. So essentially, just as a rule of thumb, so essentially, basically your zero is basically your guiding star. So as soon as the 95% confidence interval is overlapping the zero, there's no significant differences between the respective differences. So only the 95% confidence interval essentially shows you that there are differences between the respective group comparisons. So here this would be blend, a little cut off. But if you compare here blend 5 versus blend 1, you see here a significant difference. So that's a pairwise comparison. And this is basically what a Tukey does. So it's one of the ways how to approach pairwise comparison. You also can use Bonferroni pairwise comparisons where you adjust the p-values for the number of comparisons that you actually compute. And Tukey in essence does somewhat a comparable approach by calculating the so-called Q in your comparison. So, so Shital and Tracy, is this to some extent helping with the question? Or are there more specific questions?
Sorry, Professor, can you just review the diagram again? So you're saying if it overlaps with the zero, then it has no statistical significance?
If the 95% confidence interval overlaps here the zero, which is the difference between the groups, then there's no significant difference between the respective pairs. So you have blend 5 versus blend 1. Here you see that the 95% confidence interval does not overlap the zero. That means that there's a statistically significant difference between these two groups.
Okay, thank you.
Yeah. When you think of it, it's basically like it's the same principle as if you would interbreed an independent sample t-test. So you get basically, you take samples from one group, you take a subsample from the second group, you take these two subsamples that you randomly have chosen, you calculate the difference, you keep the difference, and you drop the samples back, and then you drop another sample, and you do this an infinite number of times. That basically gets you then a certain probability that you essentially see that difference between those two groups for a real systematic reason, or just due to pure chance. And this pure chance is essentially, this is your alpha level, which essentially is covering the both sides of your distribution of differences. And now these are basically on this side and on this side. So here 2.5% probability that this is just a random leftover chance or error, sampling error, for example, that you essentially see this difference between your means. group 5 or blend 5 and blend 1. So this is true for each comparison, and you're comparing it for each comparison in a pairwise fashion. So you have basically, with multiple testing, you have an exponentially increasing risk of a type 1 error. And you're counteracting that by looking at this by computation of a so-called Q, which kind of constitutes kind of an adjusted metric that takes into account that it is subject to multiple testing. So this is what tachyon significant difference test does. Just like the Bonferroni adjustment, you basically you're minimizing your p-value in accordance with the number of comparisons that you do. So you're fiddling with your alpha level to some extent. Not really with the alpha level, actually with the p-value. Your alpha level remains the same, but you're adjusting your p-value estimate and your probability of seeing this difference between the two groups just by pure chance by the number of comparisons. And that's the principle of a tachy. Does that make sense?
Sort of, but I understand how to read a diagram now, which was my original question. So thank you.
But does it answer your original question?
Yes, thanks.
Okay, great. Okay.
Professor?
Yes.
Professor, could you please go to ANOVA GFIT1, the results for that?
ANOVA fit G1, GFIT1, this one?
Yes, yes. So in this one, just reading it without looking at all of the previous data and models we've seen, I was confused looking at this because it shows model 2 as being insignificant with a high p-value from the on the right, the 0.3387. So I was interpreting that as the blend not being significant. That was my confusion.
Yes, thank you for asking this question. And that's also, this is important, the interpretation of these ANOVAs. So essentially with these ANOVAs, you're not comparing whether one model predicts something significantly or not. So it's not an R-square value, essentially. So what it really does, it compares the prediction of both models. So it really compares how accurately did model 1 predict the yield based on treatment and blend, and then takes model 2 that predicted the yield only with blend. And so the distinguishing factor here is really the treatment. And by inclusion of treatment, you have not improved the performance, not significantly improved the predictive performance of your model, which essentially means that there's no interaction between treatment and blend. So the inclusion of treatment has not significantly improved your prediction of the differences, and the differences that you see between the various subgroups are caused by blend rather than by treatment. And this is what this p-value really stands for. So it compares the models.
Oh, okay, yeah, that's very helpful, Professor. Yeah.
Well, I'm glad to hear because it's interesting, because here you do the same exercise with yield, treatment, and blend, and you try to compare it to yield and treat only. And here the distinguishing factor is blend. And adding blend to model 1 essentially has now improved your predictive quality of that model significantly. And this is what this p-value from this ANOVA essentially looks at. So it compares both models.
Oh, okay, yeah, that really helps, Professor.
Okay, great. So this is also what the question means to explain. So is the main effect of blend significant? So is it really blend or is it treatment? And this is the answer that this model comparison actually means to give. Okay. Great. So I hope this makes things a little clearer. Are there any other questions from anybody on the call? So by the way, they have more joined. Welcome. Hi, Zoe and Famit. Was this helpful in explanation? Are there any other questions? Because then we could go to lecture 6 and quickly talk about the Huber-White. So we are. So we have with Huber-White, and this is the beta star, and Shitar, you asked the question, right? So essentially what you mean to do here, I'm trying to zoom in a bit. Okay, so you essentially here trying to counteract the fact that you have heteroscedasticity in your data. So you basically, so here you see that these errors are basically differing, right? It's never really very clean. It's never very clear to judge that, right? It's like you always need to map out data. You always need to use visual inspection to actually come to this conclusion whether something is of constant variance or not. So there are statistical tests to do that. I forgot the name of the test. I think that Durbin-Watson is one of those tests where you actually can test whether these residuals of your prediction are essentially normally distributed. So when you see now something like that, which clearly does not have homoscedasticity and clearly changes here, the higher you get to higher magnitudes, it clearly shows that there's a difference in variance as opposed to the smaller magnitudes. So you have a workaround to that, which you would do only in comparison to your original analyses, and you use it. So I've to be honest, I've only seen it more in like a confirmatory version, because you lose some interpretability of some of the components, at least for the more like, how should I say, the easier methods to use. So that may not be true. But if we look now at these comparisons, and this is where the better asterisk is coming in that that Shitar was inquiring about. So this is really a different estimate as opposed to that from the ordinary least square estimation. So you basically, you get still comparable kind of estimates. So the estimates thankfully don't differ much, and they usually also don't, but you get a more quote unquote realistic estimate of your variance that is taking into account that your variance is not linear. So your variance is not homoscedastic. So it changes with change in magnitude, which is essentially quite a somewhat a proportional error, basically, that changes with the magnitude of the parameter you're actually trying to predict. So this being said, this gives you new estimates for each of your studied predictor variables and independent variables, including the intercept, and it gives you a new estimate for your actual standard errors. And therefore, you can essentially estimate the variance of your model more accurate. Let's say, call it accurate. And this is essentially, it follows the same outline, but the estimates are essentially designed in a different way that actually make it more accurate. And I think this is pretty much explaining what needs to be understood at this point in time. Does this to some extent address your question, Shitar, or do you have any questions in addition to that?
So the beta star is basically a non-linearity when we're referring to a covariate.
Correct. So this means essentially that you have a nonlinear, you have had to develop a nonlinear model that basically uses the Huber-White robust standard error that essentially allows you a more how should I say, more accurate estimate of the variance. That's the idea of this estimation method. And this is the reason why this is labeled as an asterisk, that it's obvious when you depict the model estimates that these had been developed with a method that is at variance to the common ordinary least square estimation method. But that's not a general rule of thumb. It's just one way to depict it. So you can depict it in different ways. But here it's depicted essentially to show these differences between test 1 and test 2. Was this what you meant? Or were you referring to the estimates here that basically refer to the asterisk of the p-values?
No, it wasn't about the p-value.
It was this better estimate, right?
Yes, the star
Yeah.
above the beta.
So
yeah.
this refers to the fitting method that comes from the Huber right here.
Oh, okay, great.
Okay. All right, thank you for your question, Shitar, also Tracy. Any other questions from anybody on the call? Sorry, Famid, any questions?
Good for now, thank you.
Okay, great. Famid, question from your end? Okay. So how are things? What? There's something in the chat. Okay. Okay, good. Okay, if no other questions, then we can also talk about the more technical aspects concerning. Okay, so homework. I hope this was no bigger problem, and I think the exercises were helpful on basically understanding the principle and also reviewing the principles. So the midterm exam is out, which is exam 1. So basically, it's all classes from 1 to 7. I know I said something different on the lecture, but I've revised that, and I hope everybody's aware. I think all the information is given on Blackboard. If there are any questions, you can answer those. But I wish you good luck. I'm sure you're gonna do well. It is open book, so you can use your slides and the book. But I'm sure you're gonna figure the questions out without much problem. Research note 1 is out. Please have a close look at the research note, develop a hypothesis, and then get started on coding. So this is actually where the first time you will be coding your first analyses. And I will understand that you will anytime and be help with that. So please reach out via discussion board with questions and make sure that you utilize the codes from the R&D files from the lectures as well as the lab codes. And all the answers that you may have about how to analyze things are basically contained in those codes. So let me know if you have any concerns or questions. I'll try to be as observant with the discussion board as my day job permits, but I'll try to be considerably responsive, and I hope there were no problems so far. Any questions? Yeah.
I was actually in the class 4 PDF. There was a question about whether we needed to interpret the coefficients associated with dummy variables. I think it said 0.167 and negative 4.422 doesn't need to be interpreted. It was on one of the slides.
Could you help me with locating me the context, or? Doesn't ring a bell yet.
I forget what slide it was, but my question was, do we not interpret those coefficients because they're dummy variables, or do we not interpret them because they're confounders? Yeah, that's the slide.
So these two, was moving it to interpret this in -0.617, and well, why would you not interpret them?
I was thinking that they're coefficients of R1 and R2, which we just kind of put there for convention's sake. So I thought the answer was no, but please feel free to correct me.
Well, so we want to develop essentially a model that allows for the prediction of blood pressure, right? It really depends on the context, and I'm not sure in the context I would very much think that we should interpret or coefficient. But again, it depends on the question. So if your question is now, it depends on the reference value, right? So if you have here not high school graduate and a high school graduate, which is R1, or a college graduate. So essentially, if you have a non-high school graduate, you do not need to take this into consideration if it's non-high school graduate, because you will add for a high school graduate, D1, and for a college graduate, D2, you will add a 0. So these two will fall out because your reference group is the non-high school graduate. And I think this is the context in which you're asking. So you still should interpret it because you understand that there are differences in high school graduate as well as college graduates in terms of blood pressure. But if the prediction in question is a non-high school graduate, then you do not need to really consider them in your analysis, because it will essentially render these two coefficients to be multiplied by 0, and that's when they will drop out from your prediction. But the fact that both high school graduates and college graduates do essentially have a lower systolic blood pressure is still valuable information, right? So I think this is the answer for this question.
Oh, okay, great. Yeah, that helps.
Yes, so it's really pay attention to whatever is being presented to you in any question. What is your reference group, right? And because your reference group does not need to be considered here in the calculation. Only when it's quote unquote mathematically operative, by basically giving you a 1 for R1 or a 1 for R2, then it needs to be taken into consideration in your estimate. But it still needs to be being taken into account. What I first thought that you were referring to is clinically significant differences or insignificant differences or small significant differences. So I thought you meant something like this because I remember making a comment on one of the classes in that regard. And I think there's also one on one slide, this is mentioned by Professor Sang. So particularly when it comes to large data sets, and you will see that with the enhanced data set, when it comes to large data sets, it's very quote unquote frequent that you will see significant differences. The problem with this becomes, it's really not anymore around getting a significant p-value. This is actually with large data sets quite frequent. You really need to pay attention to your actual estimates, which will give you insight of whether this is actually relevant finding or not. Because so this, for example, this does play a difference. But when you think of blood pressure, right? So blood pressure of 4.4, that's quite a difference. But now let's imagine this blood pressure estimate, which you need to take into account, is 0.004, which could, in a very large data set, very well still be significant. Because just for the reason of sample size, your p-values get very, very small because your estimates gets more and more accurate. And that's sometimes a problem because you need to really take into account what is clinically, what is significant and relevant in the greater scheme of things. It's not only about the p-value, it's also about the magnitude of the actual estimate that indicates the differences between groups, for example. So, but yeah, important points. So thank you, Shitara, for asking the question. I hope I was able to address it appropriately. Are there any other questions? So then we can maybe then transition over to the more technical part. And I see that Daryl is on. Daryl, was my response on discussion board, and my apologies for being a little late in the game to respond to that. Was this helpful? Did that resolve your problems?
I didn't go back to it, but although I did submit the assignment, I didn't return back to the discussion board because I was working on an assignment. So, but I'll go back and look at it, and maybe it could be helpful for the other assignments going forward.
Absolutely, please let me know. So one of the major things is to keep in mind, firstly, whenever you want to address something, so when you do a set working directory and you say, okay, I want to go to CW, standard-wise, it's like, I don't know, desktop, and I don't know what the exact data structure is, XYZ. It's important that when you have a Windows folder structure, that you go and take this, so you have a backslash and you have a slash. And I know it sounds annoying having to change that, and it actually is. So I also work on two different systems. I have a work computer on Windows, and I have my private computers on Mac. You need to replace your backslashes with slashes, and that usually resolves all your problems. If it doesn't, let me know.
Oh, okay. So change the backslashes to /.
Yes, it's a little annoying, but yeah, it is. So background storage R is Linux based, and Linux doesn't like backslashes. So you just gotta change it. The second thing is if else. So if else is a function that essentially tests for criterion. So if you say if else blend equals 1. So this is a criterion, right? So you do a double equal sign, and the double equal sign essentially indicates to R that this is a criterion. You're using it for logical operations. So you do either true or false. And if it's true, you give it a 1. If it's false, you give it a 0. So what I've seen in what you posted, you were missing this guy in the end.
Okay.
So it is imperative that true and false needs to add up to 100%, and or your negated resultant and your positive resultant, what's true, and the negating resultant, which what's not true, what's false, needs to add up to 100% of this criterion variable. So I think that should solve your problems.
Okay. Thank you very much.
You're welcome. No problem. Any other questions?
Professor, I just have a question. I have a couple questions actually.
Couple of questions. Okay.
One, it says that if basically the exam is similar to homework assignment 1, right? If we're able to kind of understand that, would be okay for the exam, or is it going to be a bit more challenging? Because I know you mentioned the exam is pretty challenging.
Well, it's not an easy exam. Well, if you did well on the homework and you're on top of everything on the homework, I think you're going to be fine on the exam. But keep in mind that class 7 will also be part of the exam. So that wasn't really part of the homework. So I think you will be fine. If you followed along and you understand the material good enough, you will at least know which slide or which PDF to find the right answers. It is, if you have a good solid understanding of the material, you're going to be fine. I'm not concerned. I hope this kind of
Yes.
Okay, great.
My second question is for lecture 7 on slide 21.
Which lecture? 7?
Yeah, slide 21. Can you just review that slide again?
Yeah. Slide 21, yeah. Okay. So, okay, confounding in general. Confounding in general will basically be caused by an additional third variable that associates with the exposure as well as with the outcome. So if you are studying something in an RCT, this could be essentially anything in your baseline characteristics. So let's. So I'm from the clinical realm. So let's kind of go in that regard. So let's assume you want to study something. Let's assume the effect of I don't know, vitamin C administration or vitamin C ingestion on lung cancer. Random example, but I see smoking. Okay, let's do that. So let's assume that smoking is to be considered as a confounder, right? So while vitamin C could hypothetically change some of the adverse effects of smoking, it's clear that smoking has a very strong effect on the outcome on lung cancer. So now let's assume that you would like to take this into account when you study your pathway between vitamin C administration and lung cancer. So you would like to have no confounding effect of smoking. So one way to do that is to adjust for smoking, which is problematic for various reasons, because you will have misclassifications, and you probably know after epidemiology classes a lot about this. So misclassification would lead for you to believe that one of the persons in your vitamin C group would hypothetically classify as a smoker, although he is actually not a smoker. No, the other way around. So he would classify himself as a non-smoker, but he's actually a smoker. So that would be a misclassification that actually has ramifications. So one way to deal with that is to take this confounder out of the equation. And the most reliable way of doing that is essentially to create a randomized setting. And a randomized setting will give you a maximal probability that your confounding variable is equally distributed between both groups. Because thereby, you take this effect of your confounder out of that equation. Because you don't need to pay attention to that, because you have an adequately sized study cohort that is distributed in either receiving the intervention or not receiving the intervention. And therefore, the effect will be equal in both groups. So therefore, you can, in this estimate on a population level, take this out of the equation, because it will make no difference in your estimate of the beta one, which essentially is your assignment to the treatment. So this is essentially what this wants to emphasize. So if the correlation between x1 and x2 equals 0, which would be the case if it's equally balanced between both groups, then you essentially can drop your confounding variable. So usually you would not adjust for covariates in a randomized setting. So if you have and perfectly randomized RCT, which is a problem by its own right, but in a perfectly randomized RCT, you should not have to worry about confounding. And in the simplest, and Dr. saying is making the case somewhere. So in a perfect case scenario, in a perfectly balanced RCT, you could hypothetically just compare the frequency or your outcome just using a sample t-test. or just a comparison of rates without having to pay attention to confounding. So this is what is being met. So it's basically equation 1, where you take your beta 2 into account, beta 2x, x2i. You can actually drop this under the assumption that this correlation equals 0 and it's balanced between those groups. Does that explain this slide a little bit more in detail?
Yeah, so I see that the strength of the RCT is because of the randomization. This is mathematically showing
Correct.
us how that works.
Yes.
Okay, great.
Yeah.
Thank you.
And it also, you don't need to pay attention to it analytically, which is the beauty of it, because analytically it's hard to take things into account. And smoking is a good example, because every smoker lies about smoking habit, right? And so that's kind of, that's a tough one. It's actually really make sure to incorporate it reliably and well into your model. That's a particularly good example.
Thank you.
Okay. Well, thank you for the question. It's a great question. Any other questions? If not, then I would say I'm again going to be online on Wednesday. So if there are any other questions, please come on again. And so next week I will be traveling. I will have a review session on Monday, but I will unfortunately not be able to make it on Wednesday. But I will try to find an alternate date. It's a little tricky with me now. Moving forward, I'm traveling starting Tuesday next week. But I will do my other best to still have review sessions, and I hope you can join live. And by all means, post questions on the discussion board, and I will take them on in the review session. So I will do everything to support it to the best I can. And I will definitely be also happy to schedule one-on-one calls if there are any specific questions that can be of any other help. So I'm not going to disappear from the radar. I'm still going to be around. If not, then see you on Wednesday, and let's good luck on the exam if you take it before. Don't wait till the last minute in case there are any problems coming your way. And yeah, good luck on everything, and be in touch in case you have questions about research node, the potential hypothesis. We surely can figure something out. All right.
Thank
And
you.
have a nice evening. Talk soon. Bye-bye.
All right, bye-bye.
Bye.